So this quantity, the sum of squares total, is exactly the numerator of the sample variance. So we'll write that this relates to the sample variance. So in particular, S squared, the quantity S squared, what is it? It's your best guess at the variance of a bunch of data points. It's the best guess at, well, let me say that more carefully. It's the observed variance of a bunch of data points is your best guess at the variance of the population those data points were drawn from. So S squared is calculated by taking each data point, seeing how far it is from the overall mean, squaring those values, adding them up, and dividing by how many they are, -1. And we now have a shortcut for writing down that numerator. We've decided we're going to call it SST, because SST is exactly take every data point, subtract the overall mean, square them, add them up. So SST over sample size -1 is exactly S squared, which of course implies that SST can also be written as S squared minus n minus 1. So another important learning goal here is for you to be able to connect the different quantities that appear in the output when you run various models. So it's important for you to know that the sample variance is just sample size -1 times the sum of squares total. It's important to be able to find the quantities that relate to each other in the output so that you know you're not looking at just a bunch of different numbers that don't relate to each other. Rather, output from models in statistical software is actually very redundant. The quantities can all be calculated based on each other. And what you're doing right now is starting to understand how that is. Okay, and if we have to say this in kind of words, this whole quantity, I'd say it reflects the overall spread of the data set. The spread of the outcome variable in the data set, let's say it that way. Reflects the overall spread of the outcome variable across the data set. So that's equal means model. So you can do that, right? Given a data set, you can calculate the sum of squares total. The problem is that that number by itself, which in this case was 160, doesn't mean anything, right? Unless you compare it to some other numbers. So we're not done. We're gonna have to do more. The next model that we'll consider is called the separate means model, shockingly. Instead of equal means, we've got separate means. Where the equal means model was called the reduced model, the separate means model is called the full model, because now you're making the model as complex as possible. There's two groups, well, they could each have a different mean, right? So where the equal means model said, actually all these points are drawn from the same population, the two groups don't matter, the separate means model says each group is a separate population with a different mean. So let's do this residual thing again. I'm going to write down my data points. I've got 8 and 10 and 18 and 2 and 4 and 6. But now I'm going to subtract the means that are my predictions given the separate means model or the full model. So assuming the separate means model is true, if a new student walks in the door and I'm trying to guess, I make my best guess at how many extracurriculars she does, I would first have to say, hey, are you a first year or a sophomore? And if she's a first year, that means she's in group A, and my best guess at the number of activities that somebody in that group does is my sample mean from that group, which is 12. So I'm going to take 8 minus 12 and 10 minus 12 and 18 minus 12 because those are my fitted values, my best guesses for people from group A. If somebody walks in and turns out she's from group B, then my best guess for her is the sample mean from group B. Again, under this model where I say, well, I guess the two groups might have different means. Again, all these things are residuals because of the differences between the actual data points and what the model says is the fitted value for that data point. What am I going to do with these? You will be surprised to know that I plan to square them and add them up. If you don't square them and you add them up, you get 0. You can convince yourself of that if you want to, by adding numbers up. So here we go. What is this quantity? Well, in particular, it's a number. It's equal to 64. Okay, so there's the number. But what is it? Well, 64 is called, in this case, the sum of squares within. Sum of squares within. Why am I going to call it the sum of squares within? Because it's the sum of the square differences within each group. So within group A, I've taken each data point and subtracted the mean in group A. So these first 3 values reflect how much variation there is within group A, how much the points vary around the mean in group A. These 3 values reflect how much variation there is around the mean in group B. So this is the sum of the squares within each group. And this is often called SSW. Nobody ever reverses it and calls it WSS. I've never seen that. So SSW. Or you could call it the sum of squared residuals, comma, full, which is awkward, but not that uncommon. You can call it also SSR full. That's pretty awkward. There's another name for this one too that you may have heard before, which is the sum of squared errors. So the word error is often used in place of residuals. I don't really like it because these aren't mistakes. It's just a fact that there is random variation between data points. It would be a strange data set if within every group all the values were exactly the same as each other. So errors is another word. Again, this is sometimes used for residuals. But this term is often called the sum of squared errors. Just like we related the sum of squares total to the sample variance, the overall sample variance, this quantity is also the numerator of something we've talked about before. What do you think that could be?